recording. So I want to do another example from section 3.1, another tank problem. And this problem, I'm going to outline how you'll find the amount of salt in the tank at time t. So I won't go through the entire solution, but I'll go through, I think, enough of it so that when you see it in your, you'll have it. You have one problem. Like for Thursday's homework, you have one problem like this from section 3.1, and then you have like 4 or 5 problems from section 3.2, which we'll talk about today. But I think you'll be comfortable with the one problem from section 3.1 you'll get based on going over this example. So let me give you a moment to copy it down. Okay, right. And Matthew just commented that in Discord he's going to create some groups today for the MATLAB exercises. So of course your MATLAB assignments, I still need to get a few more, a few more posted, but the MATLAB assignment 1 is posted, and I encourage you to work in groups of 3 or 4. And nothing wrong with working in a group of 4. So thank you, Matthew, for that. All right, let you copy here. A question. No, Hil Hong, good question. Hil Hong says, does a group of 2 get extra credit? No, I want at least 3 or 4, because it's better. It's actually better to have input from 2 other people in your group as opposed to just 1. It changes the dynamics a little bit, and I think it's better. And I realize too that with sure, no problem. All right. And I know you're copying. I'll mention too that the homework that was due last Tuesday, the extension ended a little early. It ended early, so I've made it where the extension will last up to Friday, March the 5th. I believe at 10:45 a.m. along with the other or 10, I forget, 10:55 a.m. I guess. I forget. It's in the morning. But the point is, if you've already taken the extension for last Tuesday's exercises, you can get another one automatically, and it'll take you to Friday, March the 5th. Okay, that would be the section 2.3 exercises, the second batch, I believe. Right. Okay, so let's take a look here. So in this case, we have a large tank filled to capacity with 500 gallons of pure water. Brine containing 2 pounds of salt per gallon is pumped into the tank at a rate of 5 gallons per minute. The well-mixed solution then, okay, so the brine, mixes in with the water. the well-mixed solution is then pumped out at a faster rate of 10 gallons per minute. Okay, and so in the past, the tank problems you dealt with, the rate at which the fluid was being pumped into the tank was equal to the rate at which the fluid was being pumped out of the tank. But I think it is important that you be able to handle a problem where the rates are different. And in this case, we're talking about, you know, the solutions being pumped out at a faster rate, at 10 gallons per minute, compared to the rate at which the fluid's being pumped into the tank at 5 gallons per minute. And by the way, what eventually will happen to the fluid in the tank? Well, in this problem, what's going to eventually happen to the fluid? That's right, Zachary. It'll decrease, and eventually, that's right, and eventually the tank will be empty. That's right. So, what's the first step in doing this problem? What's the first step that we have to do?
Model the differential.
Set him up differential equation.
That's right, Thomas. We need a differential equation. We need a differential equation. So the setup is going to be like the others. We need to find the rate at which the salt is entering the tank and the rate at which salt is leaving the tank. And then we take the difference of those rates, because, you know, we're trying to find a differential equation for, you know, dA dt. Okay, the units, of course, well, the amount of salt in the tank, the units are in pounds, and time is in minutes. So the derivative has, you know, the rate has units to it, and that, of course, helps us also with finding the right differential equation. So that being said, let me go ahead then and move to the next page. Are there any questions so far? Okay. All right. So, all right, the rate in here, you have the brine solution that contains 2 pounds per gallon, and it's being pumped into the tank at a rate of 5 gallons per minute. And so salt's entering the tank at 10 pounds per minute. Naturally, the gallons here and here simplify out, leaving you with the units of 10 pounds per minute. And, you know, this makes perfect sense that salt would be entering the tank at 10 pounds of salt per minute. That's a lot of salt, but this is a very big tank, right? 500 gallons. The question now is how to find the rate at which salt is leaving the tank. Okay, and because the rate at which the liquid's pumped out of the tank is a faster rate than the liquid being pumped into the tank, there's a time dependency. There's a time dependency here. So let's look here at the rate out and how we're getting this. Okay, so first of all, you know, just like with the previous problems, well, all right. First of all, you know, you're pumping the fluid out at 10 gallons per minute, but then what's the concentration of salt? What's the concentration of salt? Well, so you have the amount, some amount that's a function of time, of salt in the tank, and then we have to divide by the number of gallons in the tank. Okay, well, how do we find the number of gallons in the tank? It's not just going to be 500 gallons, right? Because the fluid's being pumped out more quickly than it enters the tank. So what you have to recognize is each minute the tank's going to lose 5 gallons, because 10 gallons per minute of 10 gallons is being pumped out every minute from the tank, and 5 gallons of fluid is being pumped into the tank every minute. So that's a net loss of 5 gallons. Of course, 5 gallons per minute, you multiply by t minutes, that'll give you then if you take 500 minus, well, the minutes simplify. Okay, the minutes simplify here, and you're left with gallons in the denominator. Hold on, Matthew. Okay, so Matthew's wondering about the denominator right here, why you have to have minutes. Well, the units are in gallons, because, oh, the next step. Okay, all right. Well, let's first of all right, I'll take a look at that. Let's make sure everybody's comfortable here. Is everybody comfortable with the denominator here for the concentration? Let me ask you a question. All right, Matthew's good. What if after 2 minutes, how many gallons are left in the tank? Well, no. After 1 minute, how many gallons are left in the tank after 1 minute? 495 gallons. That's right, Zachary. So see, if you set T here equal to 1, which, you know, you're doing it in your mind, but that would give you then 495 gallons. What if T were equal to 2 minutes? Well, what about 2 minutes? After 2 minutes, there should be 490 gallons of fluid in the tank. It's decreasing every minute, but so this is why. And incidentally, if you had a problem where instead of water's pumped out at a faster rate than it enters, you could have a problem where water is pumped out at a slower rate than when the fluid entering the tank. Okay, so I mean, this is I'm just trying to say this can be generalized. You could have a situation where fluid gets pumped out at a slower rate than it is pumped into the tank, but the setup would be similar. But you know, you got to think about, of course, you know, the differential equation, and you know, you got to think about just the denominator there, how to write. Okay. All right. So let me see here. So now we have 10A divided by 500 minus 5T. And then I factor a 5 out of this part here. And 10 over 5 is 2. And so you have 2A over 100 minus T. So I think the math's okay there.
My problem is it should be gallons rather than minutes, because we canceled out minutes.
Oh, 1 moment here. 1 moment. No, hold on. No, look, though, but okay, good point. But let me ask you this. I'm actually glad you asked this question. So here,
the other minute, I see.
yeah, you're going to get gallons here, and they'll cancel out with the gallons there. And so it will be pounds per minute, and we want it to be. We want it to be, because I'm glad you asked that, Matthew. So dAdt, the units of that derivative for the differential equation, are in pounds per minute. And so this is a perfect example of where having the units, see, when I work it out, I put the units in there. Now, maybe the watch it videos, they don't do that. But, you know, I'm my own man, and you're your own people, own men and women. So, you know, nothing wrong with putting units in. And at any rate, we get here, dA dt equals 10 minus 2 times A over 100 minus T. Okay. So getting the differential equation is critical because you can't get you can't even do the problem without the right differential equation. Are there any questions up to here? All right, is this a separable differential equation? How are we going to solve this linear differential equation?
Integrating factor.
I agree, Michael. Integrating factor. Okay, so I'd like to go to the next page then, if we're good. And let's look at that. Okay, so here's the setup. Okay, I get the differential equation in standard form so that I can identify my function P of t that I'll use to compute my integrating factor. And of course, the initial condition, you know, in the problem, you're not like told anything about, well, you are told about an initial condition. It's just they're not like spelling it out for you, but you have to glean it from the wording. Initially, the tank has 500 gallons of pure water. So that means at time 0, the amount of salt in the tank is 0 pounds. Okay. All right, so now we do the integrating factor. So the integrating factor here is equal to e to the power of that integral. And I put in the 200 over the 2 over 100 minus t. And then I'm going to do a little substitution. I'm going to let u equals 100 minus t, du equals negative dt, and then dt equals negative du. And I'm going to note here that u has to be positive. Okay, the 100 minus t, which came from the differential equation, that quantity has to be positive, or else let me see here. I want to be a little careful here. That quantity has to be positive, because otherwise, if it were not, the rate out would be negative, and it would be like adding salt to the tank, which you're like when you pump out the fluid, and you don't, and that's not like the case. So this is okay. This is okay. And then we integrate, we rewrite the integrating factor in an appropriate way, and finally we get the integrating factor. So the integrating factor here is mu equals 1 over 100 minus t squared. All right, and I'll slow down for a moment. Want to make sure you don't have any questions. Are there any questions so far? I have a friend, a colleague at college who's, I mean, he worked as an engineer in the defense industry, and he says these tank problems are actually very important. In statistics, we don't deal too much with tanks, but in engineering applications, they come up. And I can imagine they would, you know, chemistry, for instance. Well, you'll see that later on. But all right, so what we do is now we take the integrating factor and we multiply it through the differential equation, as you see here. And it turns out that the left side of the differential equation is just the derivative of the product of 100 minus t to the negative second power times a. And if you actually do the product rule on this product, you'll see it will work. This whole part here is 2 over 100 minus 2 over the quantity 100 minus t cubed. So I mean, you know, you're going to do the chain rule when you differentiate if you want to check it, and it will be right. Okay, how many think it's kind of good to check this, to check this, particularly maybe on the next exam, a problem like this, it'd be good to check to make sure that things are working. Okay, Ann knows what I'm talking about. And it's conceivable on the next exam for parts 1 and 2, I might even give 3 hours. Might even give a little longer because the problems are a little harder that you're getting. You know, they take time to integrate and all that to do the work. And all right, may I go to the next page? Are there any questions? Okay, thank you, Andrea. Just let me know if you're copying, and you know, you can stop me and all, you know. All right, well, then on to the next page. Thank you, Matthew. So now, of course, you're going to integrate this derivative here, right? You're integrating this derivative, and when you integrate a derivative, the function comes out. And so, you know, you're integrating both sides of the differential equation, and then you can continue to eventually solve for a of t. Don't forget, you're going to get a constant, right? You're going to get a constant of integration on the right, you know, when you are done with your integration, and you have to use the initial condition that a of 0, the amount of salt at time 0, equals 0 pounds. So you have to make use of that. And but I think this will, excellent, Matthew, excellent. I mean, I was debating whether to cover this or not, but I think as scientists and engineers, the sort of the more situations you have experienced, the better for you, you know. And so all right, Christopher's good. All right, are there any questions? All right. And incidentally, the integration for this should be pretty straightforward. So, okay, I'll stop the recording.